Okay, so on Monday we had started discussing the electrostatic potential. Just as when we were discussing electric field, we said that electric field is in fact closely related with the electric force. Now, the electric field we defined as the electric force felt by a unit charge, force per charge. And so you have a set of charges, a collection of charges. They will exert a force on another charge somewhere else. So what happens is these charges create an electric field at that point. And when you put another charge at that point, the force it will feel will be just its charge multiplied by the electric field at that point. Now, a similar thing, a similar relation exists between the potential and potential energy. So again, you have a system of charges. At this point, let's say at a given point, those charges, let's call them Qi, well, one thing, they create an electric field there. They also create a potential there. So if you want to bring this charge, let's say from a point R0 to that point R, now if you move that, the potential energy of the system will change by U of R minus U of R0. This is the change in the potential energy, and this change in the potential energy is defined as the charge multiplied by the potential difference between those 2 points. So just like the electric field was force per charge, the potential or the potential difference is nothing but the potential difference is the difference in the potential energy per unit charge, as you are moving only that charge from some initial point to the final point. You see, in this example, we started this charge from somewhere over there. This charge starts from here and moves up to this point. All the other charges are at rest at the same point. They are not moving. So the potential energy of the system changes by this much. And this is directly proportional to the charge that we are moving here. We have the charge Q moving from R0 to R. So this is the Q is proportional to Q. What remains just depends on this charge distribution over here. And that is what we call the potential. If you would make a similar analogy with the gravitational potential energy, you say gravitational potential energy is defined as mgh. So if you have a mass m, if you put it at a height h, so that is the potential energy. And you define the potential energy to be 0 when h is 0. And in that case, the potential, the analog of potential in the case of gravitation is just g times h. There is no mass, just like in the potential. When we are defining this potential, we don't define it based on this charge that we are moving. It's just a property of all the other existing charges in the system. Like here, the gravitational potential is a property of all the existing Earth and of your point, which point you are evaluating it at. This is at a point at a height h. This is the potential of this point or the potential of this point. And just like the potential energy, we cannot define the potential uniquely, but what we can define is the potential difference between these 2 points. And we said that the potential difference between between 2 points is just minus E dot dl. From the point R0 up to the point R. You see, we know that the electric force is a conservative force. So if we calculate the work that we should do if we want to carry a point charge from some point to the other point will be independent of how we go from the initial point to the final point. So whether we go along such a path or along this path, the work done would be exactly the same. Just like that, the potential difference between 2 points is again defined by this integral. And again, the value of that integral is independent of how you go from this point to the final point. Most commonly, we choose R0 to be at infinity. And V of R0 to be just 0. This choice doesn't always work, but when it works, we always set V of R0 to be 0. And now we looked at several examples. Well, we looked at one example. We said that the potential of a point charge so if we have a capital charge Q over here, the potential created at this point at a distance r, we imagine the path starting from infinity and coming to that point. Since it is independent of the path, we said that, okay, let's choose the path that makes the integral the easiest. So we just chose the radial path coming from infinity to that point. And then we determined that the potential at the point r is 1 over 4 pi epsilon 0 Q over R. Now, any questions up to here? So now let me ask you a question then. We had already studied this parallel plate capacitor, parallel plates. One had a positive sigma charge, the other one has a negative sigma charge. Do you remember the electric field outside? The electric field here? The electric field here? The electric field here? Yes. This is 0, this is 0, and inside we said that the electric field has a magnitude sigma over epsilon 0. And it is pointing in this direction. These are my electric field lines. Now let me pick up a couple of points. Point A, point B, point C, and point D. Which one has the largest potential? Why? Okay, who thinks that A and B have the largest potential? Just take a moment. How would you order the potentials of these points? I will be asking you which ones have the largest potential, which points or point has the smallest potential. Well, let's start with the largest one. Which point or points has the largest potential, and why? You say ABD. Your friend has said only AB. How would you decide which one has the largest potential? looking at the distance. Well, let's see. OK, so let me put one more point. So which distance would you like to look at? All of them is at the same potential. All of them in A, B, C, D, and E. OK, that's an idea. Anybody else? Now, how do you say that 3 is larger than 1? You look at the difference, right? You have two numbers. You look at the difference. If the difference is positive, then the first number is larger. Well, we can do the same thing over here. Let's look at the potential differences between different points. Now, let's look at the potential difference between A and B. This is VB minus VA. And from the definition, this is minus E dot dl from the point A to the point B. Now, what is the direction of E? Of course, this integral, I can't evaluate this integral over infinitely many paths. But all those paths should give me the same answer. So I should choose one path, first of all. So let us just choose this straight path from B to A. Along that path, I just go from B to A. What is the direction of dl? dl is upward. What I do is I just divide this path into very small segments. dl is a vector pointing in the direction I'm moving, and it has a length, it has a magnitude equal to the length of those segments. So dl is pointing upward. What is the direction of the electric field? To the right. What is their scalar product? 0. So A and B, they have E dot dl is 0. This is 0 at every point along my path. So this integral is 0. So this tells me that B and A, they are exactly at the same potential. There is no potential difference there. Now let's look at the potential difference between A and C. Well, by definition, this is defined as VC minus VA. This time, this is from A to C, E dot dl. So I need to choose a path that goes from A to C. Any path would give me the same result, but I would choose a path that will simplify my calculation. Simplify meaning that if you look at the scalar product, either the scalar product, if this scalar product is 0, that is simple, the integral is just 0. Or if the angle between E dot dl is constant, then I don't need to worry about changing angles. The magnitude of E is constant anyway. So I will choose this path. First along the electric field lines, and then straight down. This is my path. As I said, you can choose any path that you like. All of the paths, if you calculate it properly, should give you exactly the same answer. Now, let me call that point. Let me give it a name P. So this will be equal to, well, the integral from A to P of E dot dl plus from P to C E dot dl. Well, let's see. The easier one will be this one. As I go from the point P to the point C, what is the direction of dl? It's just downward. E, the direction of E is still in that direction. What is E dot dl? It is 0. So along this line, E dot dl is just 0. So there's no contribution from P to C. Well, in fact, if I had gone to E also, I would get the 0 contribution. So the potential at C and E, they should also be the same. Well, let's look at over this one. From A to P, what is the direction of E? In that direction. What is the direction of dl? It is also in the same direction. So this is minus, the magnitude of E is sigma over epsilon 0 times dl from A to P. This is equal to minus sigma over epsilon 0, the distance between P and A, from A to P. Is this positive or negative? This is positive, sorry. This is just the length. We are summing the magnitudes of the segments, so it just gives me the total length. Well, this is positive. So this difference is negative, less than 0. So this already tells me that VC minus VA is less than 0, or VC is less than VA is larger than VC. Well, you could in fact have said that, let's imagine we have a positive charge, and I move that positive charge from C to A. I hold that charge. I take that charge from C to P, and then from P to A. Do I do positive work or negative work? From C, as I go from C to A, do I go positive work? Do I do positive or negative work? So the potential energy of the system is increasing as I take this positive charge from C to A. So that tells me that the potential difference between these 2 points should be positive from the definition of the potential difference. You see, the work that I have done has increased the potential energy of the system. So as I go from point C to A, the potential energy of the system has increased because I did positive work. So this is positive, and the definition of potential is just the potential difference is just the potential energy difference per unit charge. If this is positive for a positive charge, then this is by definition positive. Okay, so what we had concluded is the potential of the point A and B, they are the same. Both of them are larger than potential at the point C and also potential at the point E, because they are also the same. What about the potential at the point D? Is it larger than the potential at C or smaller than the potential at the point C? Larger or lower? Imagine a positive charge. You take the positive charge from the point D to the point C. Do you do positive work or negative work? You do positive work. So the potential at the point C is larger. If you are moving in the opposite direction to the electric field, the potential energy is always increasing. Because E dot dl, if dl is in the opposite direction if dl is in the opposite direction of E, then this is negative. This makes it positive. So you are always, well, this difference is then positive. Did I say it right? If you are moving in the negative, the opposite direction of E, it's always, the potential is always increasing. Okay, so if you are moving in the opposite direction, as you are going from A to C, if you are moving in the opposite direction of E, then the potential will be increasing. That's correct, sorry. If you are moving in the direction of the electric field, as you go from A to C, most of the time you are moving in the direction of the electric field. So E and dl, they are pointing more or less in the same direction, so that is positive. So here is a negative, so the potential is decreasing. Just like in the case of the gravity. If you are moving in the direction of the gravitational force, H is decreasing, So the potential is decreasing. Any questions on this example? So let me take exactly the same system. I have the same points, the same electric field. But I will be changing the question slightly. Suppose I put a plus Q charge at the point A. A minus Q charge at the point B. We had just said that the point A and the point B, they have the same potential. Now, which one has what can you say about the potential energies of these plus Q charges and minus Q charges? Are they equal? Is one of them larger than the other one? If so, which one is larger than the other one?
Potential energy of the positive charge is high.
The potential energy of this one is larger. Why? You see, the potential energy, we had defined it as the charge times the potential. We know that both A and B, they have the same potential. And so, but we are multiplying this one with a positive charge, this one with a negative charge. So this is at a positive potential, well, let's say relative to the point D. And this one has a negative potential energy relative to a charge placed at the point D. So that is why this one has a larger potential. Larger potential energy. So it's just like the case of the electric field and the force. You see, the electric field has a direction. If you put a positive charge there, the force it feels will be in the same direction as the electric field. If you put a negative charge, it will feel the force in the opposite direction. So here, okay, although those 2 points, A and B, they have exactly the same potential, that doesn't mean that 2 different charges you put over there will have exactly the same potential energy. This one will have a larger potential energy than this one, the minus Q charge. So just pay attention. Now, any questions on these? Now, let's try to calculate. Okay, up to here we define the potential energy. Let's try to calculate the potentials created by various charge distributions. Because if you remember before, we had studied, let's say, infinite wire. Do you remember the electric field created by an infinite wire? It's pointing away from the wire at every point. And the magnitude of the electric field was, if the charge density is lambda, 1 over epsilon 0, lambda over 2 pi, the distance. Let's say this is a rho. 2 pi rho was just the circumference of the circle. Now let's calculate the potential energy. Well, let us calculate the potential energy between these points A and B. Not from infinity, but from A and B. This is just a definition of the potential difference. So if you want to calculate the potential difference as you go from A to B, it's the potential of the final point minus the potential of the initial point. So that is just minus the integral of the electric field over a path connecting A and B. Again, that path will be arbitrary, whichever one you like. But it will be wiser to choose a path that will simplify this calculation. So I will choose a path that first goes, let's say, horizontally, and then straight towards the wire. And the reason why I choose this path is that as I go from A to B, I know that the electric field is pointing up away from the wire, whereas dl is horizontal, so the scalar product will be 0. E dot dl is just 0. So the only contribution will be along this path, this part of the path. So the first thing I do is divide the integral into 2. From A to that corner of E dot dl minus from P to the point B of E dot dl. From A to P, since dl and E, they are always perpendicular to each other, it's just 0. And then I have from P to B. Well, the magnitude of the electric field is just 1 over epsilon 0, lambda over 2 pi rho, and times dl. And the angle between E and dl, I have to multiply, when I'm writing this scalar product, the product of the magnitudes times cosine of the angle between the two. What is the direction of E? dl, the angle between the two? 180. Cosine of 180 is minus 1. This is just minus 1. So dl, the length, is nothing but the change in rho as I go from one segment to the other segment. And rho initially starts from the distance of the point A up to the distance of the point B. So the potential difference between the point A and B, this is minus 1 over epsilon 0, or 2 pi epsilon 0. Lambda is a constant, I can just take it out. The integral of 1 over rho, logarithm of rho, let's say rho B minus the logarithm of rho A. Yes. There is a minus over here. So there is a minus over here. Oh, there's a minus 1. Yes, you are right. So this is plus. This is plus. But now you see, if I I can only calculate potential differences, just like the potential energy. We can only calculate the differences in the potential energy. And I can just calculate the differences in the potential between 2 points. I have to choose some reference point. As I said before, usually we choose the point at a point at infinity as our reference point. But if you look at this expression, I cannot choose the point A or the point B, let's say, if you would like to choose B as your reference point. I cannot choose B to be at infinity, because then this term is just divergent. This is an example where you cannot set the potential at infinity to 0. Well, we cannot set the potential at infinity to 0 in this example, basically because since we are assuming an infinite wire, well, an infinite wire means at infinity we have charges. So that's why we cannot set the potential at infinity to 0. The same problem happens if you have an infinite plane. If you have an infinite plane, again, there are charges at infinity, so you cannot set the potential at infinity to 0. You just choose some other arbitrary point as your reference point and just assign some value for the potential at that point. Any questions on this one? Well, this is basically how you can calculate the potential if you know the electric field. But just like when we were looking at objects like infinite wires, in the case of when we were calculating the electric field, we started with the electric field created by a point charge. And then we divided this infinite wire into very small segments, each one of which we treated as a point charge. Then we just sum them all up. Well, we can basically do the same thing over here. Well, let's look at the other example. We had this ring. Let's say we have a ring of total charge Q and the radius r. This is the center of the ring. And we are, let's say, at a distance small r from the ring. What would be the electric field, the electric potential created by the ring at that point? We can just, well, we don't really know. We have already calculated the electric field, at least along that line. So we could use that expression to choose, and we choose a path that comes from infinity along this central line to this point. That would give us the potential. Or, just like in the case when we were calculating the electric field, we can divide this ring into infinitely many small segments. Each one of them has a charge, let's say dq. So we have many segments making the ring. We had already calculated the electric potential created by a point charge. Eventually, we will assume that these segments are very, very small, so they will become just points. So we know the electric field created by a point charge. So we can write the contribution from, let's say, this segment to the potential at this point. 1 over 4 pi epsilon 0, the charge creating the potential, divided by the distance. And the distance of that point, of that segment, from the point at which we are evaluating the potential, is just small r squared plus capital R squared. Then take the square root. This is the potential created by this very small segment. Now we have to add them up. The total potential, the sum of all these potentials, which is the sum of 1 over 4 pi epsilon 0 dq over r squared plus that distance. But now, for all of those segments, this is just a constant. This r is the distance from the center. So for all the segments, this small r is the same. This capital R is just the radius of my ring. So for all those segments, they are the same. So these are all just constants. So V is equal to 1 over 4 pi epsilon 0, 1 over the distance from the ring, times the integral of d cubed. But you see, this is nothing but the sum of the charges of the segments making the ring. But that sum just gives me the total charge of the ring. So this is the potential created by this ring at a distance r from the axis passing through its center. So basically, if you want to calculate the potential of any charge distribution, you have two different means of doing that. Either, like in this example, you divide your system into very small segments. If you divide your system into very small segments, each one of them behaves like a point charge. But then you know the potential of created by a point charge. Then you just sum them up. This is the potential created by a point charge. And then we just summed all the point charges making my ring. It gives me the total potential of the ring. Or, as in the previous cases, if you know the electric field created by your system by some means, by using Gauss law or just summing the electric fields created by point charges, you calculate the electric field first. If you know the electric field, you can just evaluate this integral, and that would again give you the potential of your charge distribution. Questions? Tired? Now let's see, what about the, okay, we talk about the potential, we talked about, let's say, the potential energy. What about the potential energy of a system of charges? You see, when we were talking about the potential energy, we said that if you take one test charge, move it from point A to point B, the change in the potential energy of the whole system is equal to the Q times the change in the potential between those 2 points. But that doesn't take into account the potential energy due to our existing charges. We just have an extra charge, we put it at some point, we moved it along some path to the final point. So the potential energy of the existing charges plus this additional charge changes by some amount. And that change was just equal to the charge we were moving around multiplied by the potential difference between those 2 points. Now what we are interested in is we have a system of charges. What is the potential change? What is the potential energy of all of them? Well, let's start with the simple cases. One charge, no potential energy. So we didn't, to bring that charge from infinity, we didn't do any work on the system. Let's say we have 2 charges. Then this is the potential energy. We had already calculated it to be given by, let's say, R12, 1 over 4 pi epsilon 0, Q1, Q2 over the distance between the two. If you like, you can just think of this as the potential created by the charge Q1 at that point which is 1 over 4 pi epsilon 0 q1 over r12, multiplied by the charge that we brought there. This is the change in the potential energy. Now, if we have 3, q1, q2, q3, well, the potential energy is nothing but the amount of work that we have to do in order to bring these charges from infinity. To bring the first charge from infinity, we didn't need to do any work. Now, to bring the second charge from infinity, well, we need to do this much work. So let me write the total potential energy. Then to bring the third charge, we need to do work against the force acting on this created by the first charge and also by the second charge. So we basically do work against these two forces. Well, the work that we do against the force created by the first one basically has the same form. 1 over 4 pi epsilon 0 q1 q3 divided by r13 plus 1 over 4 pi epsilon 0. Then we need to write down the work that we have to do against the force exerted by the charge q2. It has exactly the same force. The only difference is q1 is replaced by q2. And if you have 4-point charges, well, basically the same thing. The fourth charge should do work against the force created by the first charge, the second charge, and also the third charge. So if you bring the fourth charge, you just add 3 more terms here. Now let me write these in a slightly different form. 1 over 2 times q1, 1 over 4 pi epsilon 0, q2 over r12 plus 1 over 4 pi epsilon 0, q3 over r13 plus 1 over 2 times q2, 1 over 4 pi epsilon 0, q1 over r21 plus 1 over 4 pi epsilon 0, q3 over r23 plus 1 over 2 q3, 1 over 4 pi epsilon 0, q1 over r31 plus 1 over 4 pi epsilon 0, q2 divided by r32. If you look at the first term, this term, 1 over 4 pi epsilon 0, q1 times q2 over r12. That is the first line over there. But here I have just half of it, not all of it. There's just half of it. But note that there is also this term. This term is q2 times q1, r21 and r12, they are basically the same thing. They are just the distance between those two charges, 1 and 2. So half of the first term is over here. The other half is over here. So and I don't have any other contribution to the first term. Now let's look at this term. It is 1 over 4 pi epsilon 0, q1 times q3 divided by r13. Well, it is half of that second term because of this half. But the other half is already over here. And then I had q1, q3. Then I have the q2, q3 term, 1 over 4 pi epsilon 0, q2, q3 over r23. It's this term over here. Half of it is over here, but the other half is this one. So although I have these halves over here, this way of writing and that way of writing, they give us exactly the same thing. Now, what is this one? Can you identify this expression? Well, your friend is saying that it's the potential. At which point? Which one? Of 1. Speak up. Yeah, you see, I have the charge Q2. R12 is the distance of the point position of Q1, R1 from the position of Q2. R13 is the distance of the position of Q1 from the position of Q3. So this is just the potential created at the position of Q1 by the other charges in the system. If you look at this term, again, this term is nothing but the potential created by Q1 and Q3, not Q2, but Q1 and Q3 at the point position of Q2. And this one is the potential created at the position of Q3 created by the other charges, Q1 and Q2. So the potential energy of the system I can write as 1 over 2 Q1 V of, let me just use this notation, plus 1 over 2 Q2 V prime R of Q2 plus 1 over 2 Q3 V prime of R of Q3. Now what I mean, these are just the positions of the relevant charge. This is the position of charge Q1. This is the position of charge Q3. This is the position of charge Q2. Prime, I put a prime over there to mean that when you are calculating that potential at the point R, just calculate the potential of all the other charges, ignoring the charge at the position at which you are evaluating the potential. You just multiply the potential by the charge at that point to obtain the potential energy, but there is this additional 1/2 to avoid double counting. In a sense, when we have these 2 point charges, we are assigning half of that potential energy to charge Q1 and the other one to the charge Q2, and we are just summing all the potential energies. That's why we have that 1/2. Any questions? Okay, so let's give a 10-minute break, and then we will continue.